All right. Hey guys, how's it going? I'm just gonna go to the start of my talk. All right. Some people are just settling in. Just let's wait for a minute there. Hope you had a good lunch. I hope you're having a good time at Ray. All right. Cool. I'm Devansh, and we are Simplismart. We are an end-to-end MLOps platform. Since our inception, we've been working very closely with the Ray stack, trying to manage our GenAI lifecycle using Ray as much as possible. And today we're going to talk about some practical learning, some case studies that we have seen in production with Ray, some speedups that we have been able to get using the Ray stack, and how we efficiently utilize the GenAI lifecycle, Ray in the GenAI lifecycle, right? So let's talk a little bit more about that, right? Of course, most of us here, we have been working with machine learning for some time, so we must be aware of this lifecycle in some way, shape, or form, but just a quick walkthrough. Of course, you have your first step as your data augmentation and pre-processing that again you can use Ray for very easily. We're going to talk about two loops here that we go through. One, of course, is the training loop. You fine tune, you benchmark your quality, and then you train again. Of course, the second loop that we're going to talk about crucially is the optimization loop for your specific workload when you're running inference, right? This is where we crucially utilize Ray in order to optimize the workload that you're serving for your particular use case, right? And the loop then becomes optimize, benchmark the performance, then optimize again, basis of what numbers you get on the performance benchmark. And then eventually we deploy this entire stack that we've optimized on Kubernetes. Crucially, we do not use KubeRay for inference. I know I'm gonna get a little bit of hate for that here, but there are some key low-level controls that we need to utilize Kubernetes for, and we're going to talk about that a little bit down the line in the talk as well, right? And once you are, of course, running your inference stack, you can observe it, feed that data back to your data lake, and go on with the loop again, right? So let's talk about the first part of the loop, which is the fine-tuning cycle. All right. So let me just tell you a little bit about this. Is a very simplified architecture of how we use Ray and KubeRay for our training. You have your storage layers in your different data lakes or object storages, things like that. You have your tracking layers in MLflow, OneDB, etc. How we utilize KubeRay here is to make your Kubernetes layers homogeneous in terms of how you're operating your different jobs. We insert our own training backend and training loop inside KubeRay. And then we basically create a wrapper API on top of it, which the users can use to sort of simplify their API calls, etc. The way we use KubeRay and the benefits that we get from it, let's look at it from a production case study. Specifically, we're going to talk about a customer who was trying to train an image generation model, and they were failing to scale it beyond like sort of 100 million samples, right? And they went through the same loop that we all go through. Start with a single machine, single GPU, go to multi-GPU, single node, go to multi-node, multi-GPU, things like that. But of course, this becomes tedious to manage when you're going through the normal torch distributed route, right? This is where sort of Ray comes in, and funnily enough, when we are looking at the time that it's going to take them, the estimate that's going to take them to actually train on their entire data set, it was coming out to be around 600 days when we're looking at their initial setup, right? Using Ray, we were able to scale it to across thousands of nodes, which brought down the experimentation time to a more realistic number, which is approximately 4 to 5 days, right? And beyond that, when we inserted our training loop, and this transition we're talking about, we're just taking their training loop, what they were using in Torch Distributed, convert them purely to Ray-based DDP, scaling it across node, making it much easier to sort of distribute the workload. And that way it reduces significantly. And then further, we introduce our own training loop internally inside Ray, and that gives us sort of 42% more gain on top of their existing training loops. And that way we were able to reduce the time taken per experimentation from a very impractical time, which probably nobody's going to do, right? 2 years, nobody's going to wait for an experiment, to a more realistic time that helps them iterate much faster, get to a much better model quality, right? Now, of course, once you have fine-tuned your model, you move on to the inference part of the life cycle, and we'll get the first straightforward inference out of the way, which is your batch jobs, batch inference, right? Of course, again, Ray or KubeRay is particularly useful in this scenario, especially when we're seeing transcription jobs or content generation jobs running in Ray jobs as such. So much so that we have been able to scale it to a level where we're able to transcribe 1 month's worth of audio within $1 cost, right? And that's how Ray has also enabled to scale it much more cost efficiently. But batch jobs are not everything. And that brings us to sort of the most important or sort of most interesting part of this entire conversation today, which is how do you go from, let's say, a batch cost sensitive workload to a more latency sensitive, throughput sensitive, workload sensitive use case, right? And this is where we utilize Ray the most. Let's talk about it through a use case, right? So we had a customer who was building a debt collection agent. They are building a voice bot. Of course, they're using a speech-to-text, LLM, and a text-to-speech model in order to do that, right? It's a fairly straightforward pipeline. The key metrics that they were trying to achieve here is, of course, having a latency under 300 milliseconds so that it feels real-time. And of course, you want to reduce your cost per conversation, right? Now, I'm just going to tell you what we changed in the stack, and how did we change it. We're going to talk about it in a couple of next slides. Right. So basic things that we changed here, we did not change the TTS at all. We changed the LLM. We brought down the latency, TTFB, from 450 milliseconds to 120 milliseconds, and we brought down the TTFB of the streaming ASR from 500 milliseconds to 70 milliseconds. Now, keep in mind, this is the same model that we were using for the cost-sensitive batch inference workload. It's the same Whisper model, but here the requirements are extremely different, right? And this is something that we see day in, day out with different use cases, right? You have different optimization techniques, different frameworks that you can use. For example, VLLM, SGLang, TRT. When you're using LLMs, you can serve it via litserv if you're using, PyTorch, things like that. Or you can use RayServe as well. Now, when you're working with different use cases, you have a 300 millisecond latency here. You may have a 1 second latency somewhere else. There are people who are working in autonomous OS, and I don't need to tell you how fast you need to be in those cases. Every single use case, you may be using the same models or very similar models, but you're using it for different purposes. You need different latency SLAs, different cost SLAs, things like that, right? And you have different ways of optimizing these models as well. Now, just for this use case, we had another configuration available, which was the end-to-end latency was coming down to 80 milliseconds. But if you look at it, the cost increases significantly, right? That way, what happens is your cost per conversation is much higher. Your experience gets affected only a little bit. So what choice do you make? And these are some choices that we're making day in, day out when we are assembling our inference stacks as ML engineers, right? What we have done is we've simplified the way you look at the use case in 4 key KPIs, right? So your latency, cost, quality, and throughput. Once you understand what is the requirement of your use case in these 4 dimensions, you can start choosing from this grid search hell that we deal with as inference engineers, right? What quantization to choose, what GPU, what tensor parallelism, what inference techniques, things like that, right? And once you choose that, you may get different radar charts for these different KPIs. Say, for a cost-sensitive use case, you may want to go for an H100 with a TP1 configuration, but maybe for a latency-sensitive use case, you have A100 rigs, full 8 cross, and you can just do a tensor parallel of 8, right? So depending on what you want to solve, you may need to pick and choose different sorts of environments, different configurations, different inference techniques, different optimization techniques. Now, in order to solve this, we use Ray. Basically, if you look at this entire grid, it is a combinatorial explosion. There are n number of choices that you need to make. What we do, and of course, you can have different spectrums, right? For example, the previous example, you have an over-optimized stack, which is giving you a result in 80 milliseconds. You have an under-optimized stack, which is at 500 milliseconds. And you have a sweet spot somewhere at 290 milliseconds, right? Now, given all of these combinations, it becomes heavily impractical to try it out all the time, right? Now, in order to solve this, we use a very simple mechanism that we implement with Ray. We have proxies for performance of popular architectures on popular GPUs with popular optimizations. Once we get those approximate values, we can select candidate configurations that we are going to then deploy using Kubernetes, benchmark using Ray, and then select the best configuration using our own APIs, of course, with the data that the user has given. And this entire process is then automated as a Ray job. Once this runs through, you have the best candidate model from your selection of whatever configurations you wanted to, right? And eventually what you can do is you can deploy that via Kubernetes. That is what we're doing at Simplismart. We're trying to solve this grid search hell from combinatorial explosion to building a proper AI foundry using these combinations and eventually getting to a non-intuitive solution. Because generally what we've seen is when we're working with inference stacks, we're generally going through the most walked path and we're not exploring the possible combinations that are available for the optimal solution of your particular use case, right? And that's me. If you want to talk a little bit more about what we do, how we put this process into production, you can come and talk to us. We are right over there in that booth, G2. Happy to talk, happy to chat, exchange notes, and see how you are solving your use cases as well. That's me, and we're Simplismart. Thank you for your time.